Okay, so the first example I want to take a look at for the mass spring oscillator is going to be what's called the undamped oscillator. So that means we're going to first ignore any effect that friction might have. So we're going to set the friction coefficient here, B, to be 0. So now you can think about this mass is moving back and forth over a perfectly frictionless surface. And so now the only force that's being exerted on that mass is the force due to the spring itself. So now the differential equation is mx double prime plus kx is equal to 0. And let's say we've got some initial conditions. X0 would be my initial position. So at time 0, how far to the left or to the right has the mass been moved from its equilibrium position? And x prime of 0 would be what's the velocity at time 0. So we could take the mass, stretch it 1 centimeter to the right, and actually, in addition, at time 0, give it some extra push or pull. So at time 0, the mass is located at a certain position and it has a certain velocity. So let's first consider what would happen to this model here, leaving m and k as arbitrary constants for now, if we displace the mass, say, by 2 centimeters to the right of its equilibrium, and we don't give it any initial velocity. So in other words, we're going to move it 2 centimeters to the right, and then just simply let go, and then study the dynamics of how is that mass going to behave over time. So let's solve this homogeneous differential equation. So we would take a look at the characteristic equation first of all, which would be m r squared plus k is equal to 0. And then we would find the roots of that characteristic equation. So here, keep in mind that m and k, these are both positive constants. So I've got r squared, for example, is equal to minus k over m. And so since k and m are positive numbers, then taking the square root of this is going to give me something imaginary. So I'm going to get plus or minus the square root of k over mi. So we have purely complex roots. So then that would tell me my homogeneous solution, my solution here would be that x is equal to c1 times the cosine of the square root of k over m plus c2 times the sine of the square root of k over m times t. And then, given our initial conditions, we could solve for the coefficients c1 and c2. So I will kind of skip over that step, but you could verify that based on an initial position of 2 at time 0 and an initial velocity of 0 at time 0, then we would get that the value for c1 is 2. So I would get 2 times the cosine of the square root of k m times t, and the value for c2 is actually 0. So this would be our solution to this initial value problem. And so let's graph what this solution would actually look like. And so we've got a cosine function, so I'm going to graph that just underneath. And so it's going to oscillate back and forth. So it's going to start over here at its maximum value, which is 2, and then it's going to oscillate back and forth between 2 and minus 2. And the amplitude is not going to change. But this has a period that depends on the frequency. And so to find the period, we would take 2 pi and divide by this factor on the inside. So we would divide by the square root of k over m. And so in other words, the period here would be the square root of m over k times 2 pi. And so if we look at this graph, hopefully it makes sense that we're starting off at time 0, say 2 centimeters to the right, and then we let go, and the spring is going to pull it back. It's going to pass over its equilibrium position, and if we don't have any friction, it's going to wind up 2 centimeters to the left of its equilibrium, and then the spring is going to yank it back in the other direction. It's going to pass over its equilibrium and then wind up again 2 centimeters to the right. And when we don't have friction, it's just going to keep oscillating back and forth between 2 centimeters to the right and 2 centimeters to the left. And without friction, it would just continue to do this forever, infinitely. And so what effect do the coefficients m and k, the constants, have on the behavior here? Well, they really are only going to play a role in terms of the period, the frequency of the oscillations. So if we first take a look at the constant m, when m is large, that's going to mean that the period becomes larger. And actually, the frequency of oscillation, therefore, becomes bigger and bigger and bigger. So the larger that m becomes, the more time it's going to take between it going from its max to its min back to its maximum. That makes sense. If you have a really heavy mass, it's going to take a long time for it to oscillate back and forth. If we have a really small value for m, if the mass doesn't, if it doesn't have much mass, then the period's going to be really small, and actually the frequency of its oscillations are going to be really, really small. So it's going to oscillate back and forth really quickly. And for k, we kind of have the opposite picture, and that is k is telling us something about the spring. And so if k is large, that means the spring is really stiff, then that's going to give us a really small period, right? Because as we increase k, that's making the period really, really small. And so that means the frequency of the oscillations, we're going to get a lot of oscillations in a really small amount of time. So the stiffer the spring is, the faster it's going to go from its position 2 centimeters to the right to 2 centimeters to the left and back at 2 centimeters to the right. So this gives us some sense of, when we're looking at the undamped oscillator, what role does the mass and the spring have in that system. And in the next example, we're going to take a look at what role does the damping coefficient B have. So what happens now when we start to add some friction or take some friction away, how does that affect the behavior? But at least most importantly here is that when we have an undamped oscillator, then we get the motion that this mass is going to continue to oscillate back and forth between its maximum and minimum displacement values forever and never stop.